Yeah, so thank you very much for inviting me. I'm usually speaking to people that are working with bird sounds, maybe amphibian vocalizations. So it's really nice to kind of like have a speak to an audience that works on different species groups. So yeah, like Leonie already said, I'm a PhD student. I just started my third year, and my project is focusing on exploring in what way we can use machine learning to find unknown or new sounds and so or unknown species. And so the presentation title that I have for today is Deep Learning in Bioacoustics from Supervised Classification to Unsupervised Novel Species Identification. And there we go. So, like Leonie said, I'm part of the Naturalis in the Netherlands, and I'm also part of the Bioacoustic AI doctoral network, the same that Juan is also part of. So I get to see Juan in person every 6 months, which is also very nice. And I'm supervised by Dan Stowell and Baruch Ghani, for those of you who know them. And the Naturalis is a natural history museum, so it doesn't have a doctoral school. That's why my doctoral school is in Tilburg University. And I'm currently in Paris because in this doctoral network we have these 6 month secondments where we go to different locations. And currently I'm on a 6 month research visit at the Natural History Museum here in Paris with Sylvain Aubert. For those of you who know him, he's done a lot of work on acoustic indices. Um, so the motivation for my topic is kind of the question of how can AI help us to tackle large unlabeled data sets? And now the reason that's quite important is because most bioacoustic data is unlabeled, as you all are very familiar with, I'm sure. And for some reason, because expert time is limited and it's hard to annotate 200 hours of bioacoustic data in an afternoon. And so the motivation for machine learning in bioacoustics, I think, has been like reiterated by a lot of people in the past. But the question of in what way machine learning can actually be beneficial to help us maybe delve into looking at species groups that we don't really have machine learning models that are very well trained for is kind of like a question that's been targeted a lot by researchers in the past years. And the the fact is that machine learning models can definitely help us with classification, but it's a bit of a simplification, but classification is normally limited what we already know, because what we already know then permits us to annotate data, which then paves the way to train machine learning models on that annotated data. And so in that way, the question arises in what way we can go beyond that. And I know that some of the people in the audience here have been actually doing some work on that. And so I'm also really interested in looking in what way we can explore the features that machine learning models extract and going beyond classification. And that's what I'm going to speak a little bit about today. Because ultimately the question that we want to answer, or that I want to answer for my PhD, is can machine learning be used to find new sounds? And to maybe approach that, I think it's maybe helpful to just kind of like reiterate the process of how machine learning models are trained, and then we can work our way towards the way that the analysis that I do. And so the general structure of deep learning models in bioacoustics is that we have some input source and we do some pre-processing. Now, some models actually work directly with the raw audio, but most models to this day still work based on the spectrograms. So we have some pre-processing that then feeds into our machine learning model. And we can break that model down into two parts. And we can call the first part the embedding network or feature extractor, and the second part is the classifier. And the classifier then yields some output with some percentage for the classes that has been trained on. And so if we look at that in a little more detail and we see our two input forms here, then what's actually happening throughout the model is that with increasing depth, the model will learn more abstract features within the spectrogram or within the raw audio, and essentially develop a pattern recognition mechanism that's able to find certain patterns, reoccurring patterns in spectrogram, and by learning these parameters is able to detect these patterns over time and help us to classify sounds based on the training objective that the model has been given. And so the embedding network is like comprises 99% of the parameters. It's the by far the largest part of the network. And what that outputs is a single vector, or we also call it an embedding. And so that embedding for model bird classifiers like BirdNet, for example, has 1,024 dimensions, so 1,024 floating point values. And these values are the machine learning model's way to characterize the 3 second of input audio that the model received. And so different models use different input lengths, but the point of common convergence is the creation of these embeddings. And so these embeddings are then passed on to the classifier, and that's how we are able to then differentiate between the classes that we have been trained on. But this idea of the embedding, and that's kind of like the way for the model to codify the input sounds, is very important. And so just to kind of like run you through the process of how this works is, so let's say we present the model with some input sound, and hopefully you can hear the sound. Yeah. Yeah, I'm guessing you did. So we present the model with some sound. Now we know exactly what the sound is, and sometimes to explain like kind of the process of neural network inference, I like to use like a super simplified human inference. So let's say that we can separate our brain into two parts, into a feature extraction and a classification part. And then we can say that our feature extractor in our brain is kind of like can be broken down into the connection of neural strands, and then given an input sound, certain of neural strands light up. And given the combination of neural strands that are lighting up, the classification part of our brain is then inferring like, oh, okay, that's a cat. Now, in a similar way, you could say that the machine learning model, which is based on a connection of a lot of layers of neurons, when we're presenting the model with some input sound, these neurons will fire up in certain paths, and the classifier will then receive an embedding based on what the feature extractor extracted. And that embedding that's passed to the classifier will then be mapped onto the classes that it was trained on. Now, in this case, we have a cat and dog classifier, and the model is very confident that we're listening to a cat. Now, if we make this a little more challenging and we superimpose some noise onto that sound, so I'm going to play it again. So that's a vacuum cleaner superimposed on a cat. So we're all familiar with the sounds of vacuum cleaners and with the sounds of cats. So even though different neural strands light up, we still know what we're listening to here is a cat and a vacuum cleaner. Now, for a neural network, we're already getting into the domain where it is depending on what the model has seen during training time. Because while the model should still be able to notice the cat sounds within the spectrogram, if it hasn't seen any vacuum cleaner sounds during training, the classifier is limited, because even though the feature extractor extracts its features and passes that to the classifier can only speak in cat and dog percentage. And so because of that, it's actually quite a limitation, because in a way it obscures what the model actually extracts from the spectrogram. And that's why my work mainly focuses on what's happening before the classifier, and that's where we're going to zoom into this part here, and we're going to explore the embedding space. And the embedding space is essentially mapping out all of the extracted embeddings from the input sounds. And so all of these black spots that you can see here on the right correspond to, let's say, 3 seconds of audio. And our embedding that we pass to the model can be reduced to 2 dimensions with some mathematical dimensionality reduction tools. And ideally, we would hope that our cat sound, for example, is organized somewhere in the vicinity of all the other cat sounds. And then we would have like maybe clusters for the different animals, right? This is the ideal scenario. This is the ideal way of the model structuring the sounds based on the input source. But now comes the question of if we take the cat sound superimposed with the vacuum cleaner, well, hopefully it will organize it in a way, in a proximity to that cat cluster, but then also in the proximity of some anthropogenic sounds. And so if we take that even further, we arrive at the question, what does the model actually do with sounds that it's never heard before? And so now I'm going to play a sound that hopefully you have never heard before. Okay, because of in the interest of time, I'm not going to do the guessing game of what you think it is, but hopefully you have some confusion in your classification part of your brain. Your feature extraction part of your brain is still trying to kind of like organize that sound, maybe within the space of all of the sounds that you've ever encountered, and help you to decide what that could be. Maybe an alarm, maybe it's something obscure. And in the same way, the neural network is going to extract features and create an embedding, pass that to the classifier, but the classifier is not going to produce anything of value because the sound clearly doesn't fall into these categories, and the classifier is limited to the classes that it was trained on. So again, we're going into the embedding space, and what we heard was actually a bearded seal. So that was an underwater recording, and of course, the model has no way of knowing this sound, right? But that's not really the interesting question here. The interesting question is if the model, during its training time, has learned to extract acoustic features in a way that's meaningful beyond the training data that it was trained on. And if we look at the embedding space, are we able to see that the model's actually able to organize sounds even beyond the sounds that it was trained on? And like for the bearded seal sound, for example, we would hope it would be somewhere located within the vicinity of maybe animals with similar vocalization characteristics. And of course, this is a task that's very model specific, but we could say like, ideally, this model maybe creates in the embedding space an area that corresponds to biotic sounds and one that corresponds to anthropogenic noise sounds or more engine sounds. And if we now compare different models, let's say on the left here we have our cat and dog classifier that we were looking at, then we could compare that to a different model, let's say a model that was trained on general audio. Now that model would take that same input sound, so we get for each sound we get the black spot like in the left model, but the sounds will be organized in a very different way. And now we can take our sounds that don't correspond to any of the training data that the model has seen. And what I'm working on is trying to develop a way in which we can quantify how the model is able to isolate the sounds, isolate them as their own cohesive cluster, but still in the vicinity, or organize it in some comprehensive way that corresponds to maybe the fact that it is more similar to other animal vocalizations than, for example, anthropogenic noise sources. And so my first analysis was very much based on using existing models. So I'm using, I mean, there's more than 20 big models out there that have been trained with great attention to detail and a lot of training data. And so my idea was trying to use all of these pre-trained models and see in what way they would be able to cluster sounds that they haven't been trained on. And this is a conference paper that was published last year, Clustering and Novel Class Recognition, Evaluating Bioacoustic Deep Learning Feature Extractors, that I presented at the Forum Acousticum last summer in Malaga. And going beyond that, just to kind of like walk you through the goal that I see for my project is that in the end of the PhD, I want to be able to propose some method to help find unknowns, whatever that might be. But the first step is, of course, to find out which model is actually best suited as a feature extractor. So in the terrestrial bioacoustics, focusing on birds, for example, two models that are commonly used are BirdNet and Perch. And so which of these models would be best suited to actually organize the data and create the embedding space? And then on top of that, I'm trying to right now develop a clustering that helps flag potential unknown sounds, so that if we look on our embedding space here, that we can use a clustering to kind of like highlight certain sounds within that embedding space. And finally, I think with the approach like that, it's always going to be some human in the loop approach, where you're trying to build and evaluate a tool that can like help maybe flag potential regions of unknown sounds, but in the end, it's always a feedback loop where you're able to then present the potentially unknown sounds to ecologists and help to, in an iterative process, find new species. And so this section is currently what I'm working on for my current research paper, but I've been working on the last part here quite a bit, developing a tool called bacpipe, and that stands for Bioacoustics Collection Pipeline. And the idea is pretty much that to be able to do this kind of work, it was a necessity for me to streamline this embedding generation for all of the different models. And so I built this tool which allows you to pretty much create embeddings for most of the terrestrial bioacoustic or also marine bioacoustic deep learning models and some evaluation tools so you can compare them. And we have a pretty logo that goes along with it. The idea is that you have your audio data coming in, that's the inward arrow, and then you just tweak some settings, and from it you get embeddings, classifications, and clusterings. And the idea is that it creates a GUI, a general graphical user interface, and so ideally, by the end of my PhD, there'd be something like an unknown finder where you have your embedding space, you click on a point, you see the vocalization, you can even hear it, and then by working with experts, you're kind of like making the best use of expert time that can then use the machine learning perks of being able to structure these massive amounts of passive acoustic monitoring data, but you're using the expert knowledge to then kind of like have the decision process of what are we actually looking at. And yeah, so in conclusion, that's me. That's the conference paper. If you're interested to look at that, that's the bacpipe paper that was just published yesterday. And that's a repository if you're interested in using it yourself. And before I go, I'm just gonna give you a 3-minute demonstration of what that tool looks like, if that's okay, if we have enough time for that. So
You can
can you
take
give me
much more time than 3 minutes.
Okay, maybe you always end up being faster than you plan to, right? Can you give me a thumbs up that you see the backpipe dashboard? Yeah, perfect. Okay. So let me just end the presentation because that's in the background. So this is the dashboard. So this gets automatically created. All you have to do is select your the path for your sound data and which models you would like to compare. Now, I'm sorry, there's right now we're not working with bad data. We're just working with boring birds. But just to have a demonstration, what we're actually seeing here is the data set that Juan is the lead author on. This is a neuron set. So this was collected from 4 sites in Brazil. So we have tropical rainforest soundscapes. And we can see all of these different points here. And these are 33,000 points that are generated by BirdNet. And this is a 2-dimensional visualization of the embedding space of the entire Anura set data. And because we have PAM data with timestamps, we're actually able to automatically deduce the time of day, the day of year, and the different characteristics that kind of like are already just in the metadata. And because a lot of the data sets are structured in a way that we have the different sites as folders, if we look at the sounds and we structure it by the parent directory, we can actually see in what way the model organizes the embeddings based on the sites that the sounds come from. And we can then go on each site and click on them and listen to the audio and look at the vocalization. I'm going to click on a few points just to give you like an idea for the tool. And then the idea is that you're able to kind of like zoom in and maybe inspect certain sections. And I feel like it's a necessity for me to work in this way because if you work with these machine learning models, there's a huge level of abstraction that's kind of like distancing you from the data that you're working with. And to be able to see in what way any clustering that I develop is actually corresponding to like coherence in the way that these sounds share similarities, I think it's a necessity to be able to listen to the sounds and look at the vocalizations. And so the idea is that you can then really zoom into certain areas within the embedding space, visualize the data, listen to the data, and yeah, essentially use machine learning in a way to structure massive amounts of data without asking the machine learning model to take the decision process, what it is you're looking at, away from you. Yeah, and I think that's a good point to end, and I'm more than happy to hear and answer any questions. Thank you.